Good afternoon, everyone. I don't know if I can get my first slide. Yes, thank you very much. Thanks to the organizer for having me this afternoon. I've been asked to basically give you an overview of the vision of WHO when it comes to the role of sequencing for global surveillance of drug resistance in tuberculosis. And so I think this presentation flows very well from the previous one of Tim Rodwell. Just for those who are not very familiar with our global project on drug resistance, we are very lucky in TB because we have the largest and oldest antimicrobial drug resistance surveillance project globally. It's 22 years old project, and it's being continuously funded and has been really collecting a huge amount of information. This map tells you where we are now in terms of coverage of the project. We have data from 160 countries globally, and clearly we still have problems. I'm not saying this is all nice, but we definitely have problems. You see, we still have issues in Africa where we don't know anything about drug resistance. And if we look at second-line drug resistance, what Tim was referring to before, then of course here the picture is much, is really not very nice, I would say. The coverage of basically surveillance of second-line drug resistant quinolone injectable is very limited. Just to tell you just very rapidly about the survey operations, every year there are around 15 national surveys ongoing, 15 national surveys being planned. I'm talking here about developing countries, clearly, I'm not talking about countries that do have continuous surveillance systems like this country or like European countries. In developing countries, there are this sort of big national surveys ongoing every year. And at the moment, they are all based using experts as important tools in the diagnostic algorithm. It's mainly used after smear microscopy. So what is done is they still do smear microscopy, then they do expert, and so on. Some countries are basically replacing smear microscopy with expert. But we are not there yet everywhere. We have huge challenges, and the first one is with sample transport within countries, but also internationally. Shipping specimens or even isolates has become more and more difficult nowadays. And in these kind of surveys, we have 20% losses in general. 20% of our samples gets lost in the sense culture doesn't grow, it's contaminated, and this is due to the fact that you have these issues with transportation within countries. They have historically high workload. They generate a very high workload for laboratories. It's historically these surveys are based on phenotypic testing. Imagine for a lab in a developing countries that suddenly has to basically perform 1,500 or 2,000 sort of culture and DST. It's really overwhelming. They really they are really overworked. So for us, really, it's a few years that you are exploring different options, and for us, this solution is really to replace conventional DST with sequencing for surveillance. Talking about surveillance here. And this is basically it's our vision. And I now tell you a bit about where we are in this process. We had a project funded by the Gates Foundation and USAID, also with support from a TB Alliance. And we have conducted phenotypic, these are surveys in 7 countries, national surveys in 7 countries for a total of 7,000 patients, which we had the luxury to do sequencing in parallel. Okay, so you know, the table is very busy, but basically it tells you that to prove the principle, we were able to conduct sequencing on isolates in parallel to phenotypic testing. This project is over. The data are being analyzed, and I will show to you some data in a moment. This is done. This is complete. But the work is really going and is really expanding dramatically. There are already 4 countries where surveys are ongoing using whole genome sequencing. Those are very large countries like Congo, Indonesia, and then some, of course, small like Djibouti. And there you see different technologies used. In the first group, we were basically doing WGS or sequencing based on isolates. Now we are moving towards doing target gene sequencing on sputum samples. And we are using the technology which is available at the moment, of course, which is the duplex technology from GenoScreen. And this is the work which is planned. Planned means already funded, already written up protocols. It will start this year. So there are other 3 countries for another large number of isolates. Now, let me now show you a bit of the results. So, how we are going to use this data, basically, in surveillance. And for us, the first step was to basically make an assessment on the accuracy of sequencing compared to phenotypic testing for these main drugs, first-line drugs, second-line drugs. We have not yet started looking at new drugs. But clearly, we have got extremely high specificity for all these drugs, like more than 98.5%. So a very, very promising. No problem with false positive, basically. We have, of course, suboptimal sensitivity, and this is not new. This is all already, published in smaller study so what we are planning to do is to adjust to correct this data and use basically a simple model to estimate drug resistance based on genotypic data and skipping not using the phenotypic results. We are not yet there with the second point. We are basically working on it. Some of the results I'm going through very fast. Before showing the results, I'd like to say that to classify mutation, we used a grading system which has been developed by CPAT and FIND, and this will be presented, I think, tomorrow by Paolo Miotto. So I'm not going to the details of that sort of grading system, but just to say that we have not come up with a completely different system. We have just used what's available. So these are the data for rifampicin. You see there is clearly variation between countries, but overall, the pooled estimate from a random effect model is around 90%. I'm going very fast now because this is the data for INH, looking at both CAT-GA and IHA. And again, this is sensitivity, of course. Specificity, as I said, I'm not going to present, is very high for every drug. So it's around 87%. This is the sensitivity for ofloxacin, looking at GR and GRB. And you can see this is very much in line with what we know. The beauty of this data is that it's lots of strains. We have a total of 7,000 strains at the moment, coming from countries that are in very different regions. We have a problem with MOXIE, and I have also presented it, I think, a couple of years ago. We still have this problem. This is the sensitivity of GR and GRB compared to MOXIE at 2 microgram ml. And it's basically on the lower sort of you know, 73% is on the low, it's a bit low compared to what we see in the literature. PZA is the problem, but this is not surprising. And you know, when it comes to surveillance, this is not a problem. But, you know, it's really not a problem because for us, as long as we have high specificity, we'll definitely make adjustments for sensitivity. You know, the second graph shows you the data when it's adjusted for the Wayne test. So basically what we did run a Wayne test when we had strains with discrepancy between phenotypic and genotypic results. And so it improves a bit it's around 79%. It improves a bit the sensitivity. And then very rapidly, the injectable drugs, those are only among rifampicin resistant cases. What I showed you before, it was among all cases. For injectable, we decided to limit to the rifampicin resistant because from a public health point of view, there is no point to estimate, no reason to estimate prevalence of resistance to injectables to the non-rifampicin or to the rifampicin susceptible patients. It's an information that is not going to be used. So this is kanamycin, RRS and EIS. This is amikacin, it's around 90%, 91%. And this is capromycin, which is slightly lower. So for us, this is basically confirming what we know in the larger scale in the context of a surveillance setting. And we take it as a positive sort of result. We are now entering the second phase, which is going to be very rapid. It's like desk work, basically. We are basically developing a very simple model, which is using a Bayesian approach to basically adjust the apparent prevalence to come up with the true prevalence for resistance and propagate uncertainty. This will be done very rapidly. And once we have that, I think we can really see whether this sequencing can be used large scale in surveillance and replacing phenotypic testing. So this is my last slide. I was asked to talk about a bit a vision for the future. This is for us. It's a near future. I hope I made the case. It's already happening in big scale. So it's a future in 2-3 years. I think we see surveys based with expert at the entry point. Again, here I'm talking about developing countries. It's not countries like the US. And then targeted gene sequencing either from leftover from expert cartridge or from a new sputum sample. And then, of course, we will have a common sort of database to basically standardize reading and interpretation of all the data. And then estimation of prevalence of resistance based on genotypic data exclusively. So this was my last slide, and I hope we'll have a discussion later on. Thank you. Sorry, I forgot to acknowledge all the people involved. There are so many people involved, people in my team, but also countries and the donors, particularly Gates Foundation, USAID, and the TB Alliance.